Now we are at the point where we need to compute the range of this projectile launched from an incline. But if you remember how we had earlier found the range of the projectile launched from the ground, we first computed the time of flight. So this is the time of flight, right from the time it is launched to the time the projectile lands. And to compute the time of flight, we applied the second equation of motion along the y-axis. And we will do exactly this in the current lesson, except that the y-axis is no longer vertical but is perpendicular to the plane of the incline. So here we have the second equation of motion. Y minus y0 equals v0t plus half at squared. Our reference line is now the x-axis, which lies on the plane of the incline. The initial displacement y0 is 0 since it lies on the reference line. The final displacement is also 0 since it again lies on the reference line. Let's just watch the animation and you can see y reduces down to 0. The initial velocity Vy along the y-axis is now v0 times sine of alpha. The acceleration component along the y-axis is g cos of beta and its direction is opposite to the initial velocity. So it is in the negative y direction. With this, we are ready to solve for the time of flight t. The time of flight turns out to be 2v0 sine of alpha over g cos of beta. If you recollect the formula we had when the projectile lands back on the ground, it was 2v0 sine alpha over g. So cos of beta is the extra term that is introduced when it lands on an incline having an inclination of beta. So when beta is 0, cos of beta is 1 and the projectile lands back on the ground. And we get the same expression for time as we did earlier. Let's do a numerical problem so you get the hang of the role of all the variables in this formula. We launch a projectile with a speed of 70 meters per second from the base of an incline, having an angle of inclination of 20 degrees. So beta is 20 degrees. The angle of launch is 45 degrees with respect to the ground. So alpha plus beta here is given as 45 degrees. And from here we can compute alpha, the angle of launch with respect to the incline, as theta minus beta, which is 45 minus 20 or 25 degrees. Let's find the time of flight now. Substituting v0 as 70, alpha as 25, g as 10, and beta as 20 into the time of flight equation, we obtain the time of flight as 6.3 seconds, which means that the projectile remains in flight for 6.3 seconds since the time of launch before landing back on the incline. Using this value of time of flight, let's compute the range of the projectile along the plane of the incline in the next lesson. And to get to the time of flight, you have seen that we followed exactly the same procedure as we had when the launch was from ground to ground without an incline. To compute the time of flight, we apply the second equation of motion along the y-axis. The y-axis here is perpendicular to the incline. We have to be careful that in the equation we substitute the components of velocity and acceleration which are along the y-axis perpendicular to the plane of the incline.